Modules and Homological Algebra, Lecture 11, Applications of Classification of Modules over Principal Ideal Domains. Let us first recall the main result of the previous lecture, which is the classification of finitely generated modules over principal ideal domains. Let M be a finitely generated module over a commutative principal ideal domain R. Then there exists unique non-negative integers k and m, and unique up to permutation and association positive integers n1 and so on and m, and prime elements p1, p2 and so on pm in R, not necessarily different, such that the module M is isomorphic to the following direct sum. The first summand is the regular module R to the power k. And then we have the torsion summands R divided by the ideal generated by p1 to the power n1 plus R divided by the ideal generated by p2 to the power n2 and so on until the last summand R divided by the ideal generated by pm to the power n. The first application for today is classification of finitely generated abelian groups. In order to do that, we consider the case when R is the ring of integers, and we know that it is a principal ideal domain, and we also know that the modules over the integers are exactly abelian groups. So this means that each abelian group has a unique structure of a module over the integers, and that homomorphisms of abelian groups are exactly the homomorphisms between the corresponding modules over the integers. Furthermore, we know that prime elements in the ring of integers are exactly the prime numbers, so positive and negative prime numbers, and each prime number p is associated only to itself and to the number minus p. So this is because in the ring of integers there are only two invertible elements, 1 and minus 1. Now we can apply our classification of finitely generated modules over principal ideal domains to classify all finitely generated abelian groups. The theorem, classification of finitely generated abelian groups. Let A be a finitely generated abelian group. Then there exist unique non-negative integers k and m, and unique up to permutation positive integers n1 and so on and m, and positive prime numbers p1 and so on pm, such that our group A is isomorphic to the direct sum of k copies of z, together with a direct sum of the following finite cyclic groups. So the finite cyclic group of order p1 to the power n1, then the next summand is a finite cyclic group of order p2 to the power n2, and so on, and the last summand is the finite cyclic group of order pm to the power nm. And as a corollary, we can even classify all finite abelian groups. So if A is a finite abelian group, then there exists a unique non-negative integer m, and unique up to permutation positive integers n1 and so on and m, and positive prime integers p1 and so on pm, such that A is isomorphic to the direct sum of cyclic groups of orders p1 to the power n1, then p2 to the power n2, and so on, pm to the power nm. We know that if m is equal to 0, then this direct sum is empty, and by convention this means that it gives us the one-element group, the cyclic group of order 1. Here is an example. So let us determine the above decomposition for the finitely generated abelian group A, which is defined as the cokernel of the homomorphism from z to the power 4 to z to the power 3, which is given by the following matrix: 2, 0, minus 4, 2, 4, minus 2, 0, 8, 6, minus 2, 0, 0. In order to solve this problem, we need to reduce our matrix to its Smith normal form. clearly, just looking at the matrix, we see that 2 is the greatest common divisor of all entries of this matrix. So we can use the element 2 in position 1, 1 to eliminate all other elements in the first column. So we take the first row of our matrix, multiply with -2, and add to the second row. And then we take the first row, multiply with -3, and add to the third row. And in this way, we eliminate all other elements in the first column. So our new matrix is 2, 0, -4, 2, 0, -2, 8, 4, 0, -2, 12, -6. Now, for the Smith normal form, we are allowed to use both row and column operations. So now we have 2 standing in the position 1, 1, and we can use it to eliminate all other elements in the first row. So we take the first column, multiply with 2, and add to the third column. We take the first column and subtract it from the fourth column. Our new matrix will be 2, 0, 0, 0, 0, -2, 8, 4, 0, -2, 12, -6. So in this matrix, if we delete the first row and the first column, it is clear that in the remaining matrix, 2 is the greatest common divisor of all entries, or -2, because 2 and -2 are associated, so it doesn't matter which one of them we choose. So we can use the -2, which here is in the position 2, 2, and elementary row operations to eliminate all other entries in its column. So we subtract the second row from the third row, and the new matrix is 2, 0, 0, 0, 0, -2, 8, 4, 0, 0, 4, -10. And now again we can use the column operations and this -2 in position 2, 2 to eliminate all other non-zero entries in the second row. So we multiply the second column with 4 and add to the third column, and we multiply the second column with 2 and add to the last column. And the new matrix is 2, 0, 0, 0, 0, -2, 0, 0, 0, 0, 4, -10. Now in this matrix, if we delete the first 2 rows and the first 2 columns, we get the matrix with elements 4 and -10, and the greatest common divisor there is 2. So we should use some operations to get 2 out of 4 and -10. And the easiest way to do this is to add twice the third column to the fourth column. And the new matrix is 2, 0, 0, 0, 0, -2, 0, 0, 0, 0, 4, -2. And then if we swap column 3 and column 4, we will get 0, 0, -2, 4. And finally, we use this -2 to eliminate this 4. So we add twice the third column to the first column, and we finally get the Smith normal form 2, 0, 0, 0, 0, -2, 0, 0, 0, 0, -2, 0. And now we can read off the answer. So from the first component, we get the cyclic group of order 2. From the second component, we get the cyclic group of order 2. And from the third component, we get the cyclic group of order 2. So our abelian group A is isomorphic to a direct sum of 3 copies of cyclic groups of order 2. Now, the second application, Jordan normal form. So here we consider the case where our ring R is the polynomial algebra in one variable with complex coefficients. We know that this algebra is a principal ideal domain, and we know that a module over polynomials in one variable is simply a vector space over complex numbers with a fixed linear operator in this vector space which represents the action of x. So if you know how x acts using composition and linear combinations, we can determine the action of all other polynomials. At the level of matrices, change of basis in V corresponds to change in the matrix of the linear operator F to the matrix T inverse, the matrix of Ft, where T is the transformation matrix between the two bases. Also, by the fundamental theorem of algebra, the prime elements in the polynomial algebra with complex coefficients are exactly polynomials of degree 1. So any polynomial which is not constant has a root over complex numbers, and so x minus the root divides the polynomial. This means that the irreducible, and that is prime elements in our ring, are exactly the polynomials of degree 1. Moreover, two such polynomials are associated if and only if they differ by a non-zero scalar. The only invertible elements in the polynomial algebra are non-zero scalars. In other words, if we take a polynomial of degree 1 and divide it by the first coefficient, which is a non-zero scalar, we will get that that polynomial is associated to x minus lambda or some lambda. Now we can formulate classification theorem for finitely generated modules over complex polynomials in one variable. Theorem: let V be a finitely generated modules over C of x. Then there exist unique k and m, non-negative integers, and unique up to permutation positive integers n1 and so on and m, and complex numbers lambda 1 and so on lambda m, such that the module V is isomorphic to the direct sum of k copies of the regular module C of x, and then the direct sum of the following summands. So we take the regular module C of x and we divide by the ideal generated by x minus lambda 1 to the power n1. So the next summand, C of x divided by the ideal generated by x minus lambda 2 to the power n2, and so on. The last summand is Cx divided by the ideal generated by x minus lambda m to the power nm. So this is about finitely generated modules, and we can specialize it even to finite dimensional modules. If we have a finite dimensional module over a polynomial algebra, then there exists a unique m non-negative integers and unique up to permutation positive integers n1 and so on and m, and complex numbers lambda 1 and so on lambda m, such that V is isomorphic to the direct sum over all I from 1 to m of the module C of x divided by the ideal generated by x minus lambda I to the power n I. Let us describe the action of x on indecomposable modules. So our indecomposable summands are the regular summand. There it's clear how x acts. So the regular module has a basis consisting of the powers of x, and multiplication with x shifts x to the power I to x to the power I plus 1. In the finite dimensional module Cx divided by x minus lambda to the power n, we have the basis consisting of the powers of x minus lambda to the power I. And let us order this basis such that the highest power comes first, and then the power whose exponent is 1 smaller, and so on. In this basis, the action of x minus lambda is given by the following matrix. Multiplying the second basis element by x minus lambda, we get the first basis element. So the third basis element goes to the second basis element, and so on. So here we have a matrix where almost everything is 0, apart from the diagonal, which is next to the main diagonal, and there we have numbers 1. So this is the action of x minus lambda. So if you want the action of x, we should add lambda onto the main diagonal, and we get exactly the Jordan cell with the eigenvalue lambda and of size n. So we have such an n times n matrix with lambda on the main diagonal, 1 on the diagonal above it, and the rest is 0. And so we can formulate the corollaries for the Jordan normal form. So let F be a linear operator on a finite dimensional complex vector space V. Then there is a basis in V with respect to which the matrix of F is a direct sum of Jordan cells, defined on the previous slide. Moreover, such decomposition is unique up to permutation of summands. And we have a similar corollary for matrices. Let M be a complex n times n matrix. Then there is an invertible n times n matrix T, such that the matrix T inverse MT is a direct sum of Jordan cells. Moreover, such decomposition is unique up to permutation of summands. Here is an example. let us determine the decomposition for the finitely generated module over the polynomial algebra defined as the cokernel of the homomorphism from Cx to the power 2 to Cx to the power 2 given by the matrix x, x times x minus 1, x squared, x times x minus 1. Also, let us determine the dimension of this module, it should be V, and the trace on this module of the linear operator which represents the action of x. In order to solve the problem, we need to reduce this matrix to its Smith normal form. Again, clearly x is the greatest common divisor of all entries. So first, we eliminate all other entries in the first column. So we multiply the first row with x and subtract from the second row. So we get the matrix x, then x times x minus 1, 0, and then minus x times x minus 1 squared. So we will have x times x minus 1 minus x times x minus 1. We will get exactly 1 minus x there as a multiple. Great, so now we can use x in position 1, 1 to eliminate all other entries in the first row. So we do the elementary column operations. We multiply the first column with x minus 1 and subtract from the second column. And we get the diagonal matrix x 0, 0 minus x times x minus 1 squared. So this is the Smith normal form of our original matrix. From the first diagonal element, we get the summand Cx divided by the ideal generated by x. And from the second diagonal element, we get the summand Cx divided by the ideal generated by x times x minus 1 squared. Since x and x minus 1 are obviously relatively prime, we can further decompose the second summand into the direct sum of Cx modulo the ideal generated by x and Cx modulo the ideal generated by x minus 1 squared. So the first summand has dimension 1 because we kill an ideal generated by polynomial of degree 1. The second summand has dimension 1, and the third summand has dimension 2, because we kill the ideal generated by a polynomial of degree 2. Adding this up, we get that the dimension of the whole module is 4. The action of the linear operator, which represents the action of x on this module, in the standard basis is given by the following matrix. So on the first summand, x acts as 0. So we have the 0 direct summand here of size 1 times 1. On the second summand, x acts as 0 because the eigenvalue is 0 and it's 1 times 1 matrix. So it's just 0 on the diagonal. On the third summand, x acts as the Jordan cell of size 2 times 2 and with the eigenvalue 1. So it's the matrix 1, 1, 0, 1. Taking the direct sum of these three matrices, we get that this is the matrix 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 1, which represents the action of x on our module in the standard basis. And of course, the trace of this matrix is 2. And this completes the solution. And finally, the third application is the real normal form. Here we consider as our ring the ring of all polynomials with real coefficients and in one variable. And we know that this is a PID. This is a PID for any field. So we know that a module over this ring is just a real vector space V with a fixed linear operator f on V, which represents the action of x. And the change of basis, so if you want to write the matrix of f in different bases, then changing the basis using the transformation matrix T, so the matrix of f is substituted by T inverse ft. As in all polynomial algebras over fields, invertible elements in R of x are exactly the non-zero polynomials of degree 0, that is, non-zero scalars. And an interesting question for us is what are the prime elements in this ring? Of course, all polynomials of degree 1 are irreducible, and so they are prime. But over the real numbers, here is another example of an irreducible polynomial, x squared plus 1. So this is a polynomial of degree 2. If it would be reducible, it must be a product of two polynomials of degree 1. And so a polynomial of degree 1 always has a root. But this polynomial doesn't have real roots, so it is irreducible. So we have more irreducible elements in the polynomial algebra over real numbers than just polynomials of degree 1. So let's classify them. Proposition: any prime element in R of x is associated either to a polynomial of degree 1, which means to a polynomial of the form x minus lambda, where lambda is a real number, or to the following polynomial of degree 2, to the polynomial of the form x squared plus ax plus b, or some real a and b, such that a squared minus 4b is strictly smaller than 0. Proof: let f be a prime element in R of x. Let lambda be a root of f of x in C. Of course, f of x is a real polynomial, so it's a complex polynomial. It has a root in C. If this root happens to be a real root, then x minus lambda divides f of x. And since f of x is prime, f of x must be associated to x minus lambda. If lambda is not a real root, then the complex conjugate of lambda is a root, because f has real coefficients. Then the product of x minus lambda and x minus lambda complex conjugate is a polynomial with real coefficients, and it divides f of x, and hence it must be associated with f of x. The polynomial x minus lambda times x minus lambda overlined has the following form. So it's x squared minus 2 times the real part of lambda plus lambda times lambda overlined. So our condition a squared minus 4b should be negative, should read now as lambda overlined plus lambda squared minus 4 times lambda lambda overlined. And this is equal to lambda overlined minus lambda squared. Note that lambda overlined minus lambda is a non-zero multiple of the imaginary unit I, so its square is strictly negative. And this completes the proof. And as usual, we denote by bold I the imaginary unit in the complex numbers. So now we can formulate classification of finitely generated R of x modules. Let V be a finitely generated R of x module. Then there exist unique non-negative integers k, m, and l, and unique up to permutation positive integers n1 and so on and m, r1 and so on rl, real numbers lambda 1 and so on lambda m, alpha 1 and so on alpha l, and non-zero real numbers beta 1 and so on beta l, such that our module V is isomorphic to the direct sum of k copies of the regular module Rx, and then we have m different summons of the form R of x divided by the ideal generated by x minus lambda I to the power ni. And then we have L direct summons of the form R of x divided by the ideal generated by x squared minus 2 alpha ix plus alpha I squared plus beta I squared to the power ni. Please note that for these last direct summons, the polynomial x squared minus 2 alpha x plus alpha squared plus beta squared, this polynomial has non-real complex roots alpha plus minus beta I, provided that beta is non-zero. So this is how we use this condition that betas are non-zero real numbers. In order to formulate an analog of Jordan cell decomposition over R, we need to define the so-called real cells. So let alpha and beta be real numbers with beta non-zero. Consider the module R2 over the polynomial algebra, on which the variable x acts via the matrix alpha beta minus beta alpha. It is straightforward to compute that the characteristic polynomial of this matrix is exactly x squared minus 2 alpha x plus alpha squared plus beta squared. In particular, using the Cayley-Hamilton theorem, we see that m squared minus 2 alpha m plus alpha squared plus beta squared annihilates our module R2. Therefore, by factorization lemma, and using the fact that R of x, the regular module, is free, so the free property of the free module R of x says that given any element v in R2, there is a unique morphism from R of x to R2, which sends the generator 1 of R of x to this element v. But now we know that this expression annihilates R2, and so by factorization lemma, this map factors through the quotient of R of x by the ideal generated by this polynomial. Note that the image of this homomorphism cannot have dimension 1 because our matrix M doesn't have real eigenvalues. So therefore, the image of this homomorphism, if V is non-zero, the image of this homomorphism must have dimension 2. So it's surjective. But then the original module also has dimension 2. So since both modules have dimension 2 and the homomorphism is surjective, it means that it's an isomorphism. As a corollary, now if we take the quotient of R of x by the ideal generated by such polynomial to the power n, then in this quotient there is a basis in which the action of x is given by the following 2n times 2n matrix. So we have here on the diagonal the 2 times 2 blocks, which are equal to our matrix M from the previous slide. And just above the diagonal, we have the identity 2 times 2 matrices. So if we subtract the diagonal blocks, we will get exactly the nilpotent element of degree n. So we denote this matrix by R to n alpha beta, and we call it a real set. So note that this is 2n times 2n real matrix. And now we can formulate the real normal form corollary. Let F be a linear operator on a finite dimensional real vector space V. Then there is a basis in V such that the matrix of F in this basis is a direct sum of some Jordan cells with real eigenvalues and some real cells. Moreover, this decomposition is unique up to permutation of summations. At the end, some problems and questions. Problem 1. Determine the decomposition for the finitely generated abelian group A defined at the cokernel of the homomorphism from Z2 to Z2 given by the matrix minus 6, 9, 9, minus 12, 27, 3. Question 2. Determine the matrix of the action of x on the module R of x divided by the nth power of x squared minus 2 alpha x plus alpha squared plus beta squared in the following basis. So we take all powers of this polynomial, all powers from 0, 1, and so on up to n minus 1, and then all these powers multiplied by x. Question 3. Determine the matrix of the action of x on the same module in the basis given by the powers of x. So the basis 1, x, x squared, and so on, x to the power 2n minus 1. Question 4. Fill in all the details into the proof of the real normal form. And question 5. Classify finitely generated modules over the Laurent polynomial ring CT T inverse. Thank you very much and see you next time.